Chapter 2, Exercise 18. Hence, enumerate all rational numbers in a sequence this, and repeatedly remove open intervals with rational centers and small enough lengths. Solution. Yes, we will construct such a set. The set Q of all rational numbers is countable, corollary to Theorem 2.13. Hence we can enumerate all elements of Q into a sequence this. In what follows, we construct a sequence of open intervals this, with rational centers and small enough lengths. The needed set E will be defined as this. Intervals ik will be constructed inductively. Let us fix a positive irrational number a, for example a equals square root 2. Define the first interval I1 as follows. I1 equals this, where n1 equals 1, m1 equals 1. Assume that intervals this are already constructed in such a way that these intervals are disjoint. Their endpoints this are irrational, and their union this contains rational numbers this. Let nk be the first index such that this. Note that this, as the numbers this, are irrational. The set this is closed, Theorem 2.24d. Hence there exists epsilon greater than 0 such that this, Theorem 2.23. By the Archimedean property, there exists an integer m such that 2 to the m greater than a over epsilon. See the similar argument in example 17. As 2 to the power m is increasing with m, we can take m greater than or equal to k. Hence there is an integer mk greater than or equal to k such that 2 to the power of mk greater than a over epsilon. Define ik equaling this. We note that ik subset of this, since epsilon greater than a over 2 to the power mk, so that intervals here are disjoint. Endpoints of the interval ik are irrational, as a is irrational. Further, qk element of this. Indeed, this is obviously true if qk element of this. If qk not element of this, then, since this, k is the first index such that qk not an element of this. Consequently, this and this. Summarizing, intervals this are disjoint, their endpoints are irrational, and their union this contains rational numbers this. This means that our inductive construction can be continued. For an open-closed or half-open interval j with endpoints a, b element of R, by the length of j we will of course understand the quantity m of j equaling absolute value b minus a. Note that at every step we constructed an interval ik of length this. Our inductive construction produces a sequence of intervals this such that I, for any j not equal to L, this, II, endpoints of each interval ij are irrational, III, the length of each interval ij is this, IV, for each integer k greater than or equal to 1, the union this contains that. We define the set E equaling this. The set E is closed and it is the complement of an open set this. Theorems 2.23 and Theorems 2.24a. Since for every integer k greater than or equal to 1, q of k element of this, this set E contains no rational number. Let us show that the set E is non-empty. Assume the contrary. Then this. In particular, this. The set negative a to a inclusive is compact, Theorem 240, so its open cover this contains a finite subcover this for some n greater than or equal to 1. Now we shall prove an auxiliary result. If a closed interval j is covered by open intervals this, then this. Recall that mj is the length of j. We will prove the statement by induction on n. Let n equal 1. If a closed interval j equaling this is covered by an open interval g equaling this, that is, this subset of this, then beta less than b and c less than gamma. Hence, this and this statement is true. Assume that our inductive hypothesis is true for n-1 and a closed interval j equaling this is covered by open intervals this. Since this, there exists m in this such that c element of gm, that is, beta of m less than c less than gamma of m. Without loss of generality, we can assume that m equals n. Otherwise, we can enumerate the sets. In other words, beta of n less than b less than gamma of n. If beta of n less than b, then m of j equaling this. Hence, assume that b less than or equal to beta of n less than c less than gamma of n. We note that this, hence this, by our induction hypothesis, this. It follows that this. The auxiliary statement is thus proved. Since this, it follows that 2a less than this, which is impossible. Here, we use the formula this. The obtained contradiction shows that the set E is non-empty. It remains to prove that the set E is perfect. Since we already proved that E is closed, we need to show that E contains no isolated points. Let us note that for every integer ik equaling this, it holds that L of k, I of k, element of E. Indeed, assume that L of k not element of E. Then this, and there exists j not equal to k such that this, then L of j less than L of k less than I of j. Consider a real number t such that t greater than 0, and this. Then this and that. It follows that this, which is impossible since this. Similarly, if ik not an element of E, then this, and there exists j not equal to k such that this. Then L of j less than I of k less than I of j. Consider a real number t such that t greater than 0 and this, then this and that. It follows that this, which is impossible. Assume that x in E is an isolated point of E. Then for some epsilon greater than 0, this. In particular, this, meaning that this. Hence, there exists an interval I of j equaling this, such that this, it follows that this, indeed, assume that this, then either x less than L of j, or x plus epsilon greater than I of j. Consider a point this. If x less than L of j, then x less than L of j less than y and this. This contradicts the fact that L of j in E. Similarly, if x plus epsilon greater than I of j, then y less than I of j less than x plus epsilon and this. This contradicts the fact that I of j in E. So this implies that this. If L of j less than x, then x in ij, but this is impossible as x is in E. So x equals this. Proceeding in the same way with the interval here, we see that for some interval I of k equaling this, this, and that. Thus we have shown that this. From here, this, Since q and j and q and k are rational numbers, we conclude that a equals this. But this is impossible as a is chosen to be irrational. Obtained contradiction shows that E contains no isolated points and is thus perfect. Here is a picture. First, the intervals to be removed in our construction when n1 equals 1, n2 equals 4, and n3 equals 6. Comments. Perfect sets such as closed intervals this, closed rays this and this, the Cantor set P, and the set from example 17 all contain rational numbers. For example, 0, 1/3, 2/3, 1 belong to the Cantor set. Rational numbers 4/9, 7/9, 47/99, etc. belong to the set from example 17. This exercise shows that perfect sets can have more complicated and strange structures. During the solution of this exercise, we have established an important fact in measure theory. If a closed interval J is covered by finitely many open intervals here, then this, where m of j denotes the length of the interval J. Since closed intervals are compact, this result extends to the case where J is covered by an infinite sequence of open intervals this, yielding this. The discussion of infinite series can be found in Chapter 3 of this book. Thanks for watching.